education. You can always get a master's degree, you know. Probably don't need it right off the bat. The market's so hot right now. Just, I think there's lots of opportunity out there. You've got until 11:59 to finish that design project number 2 assignment. And I haven't gotten any recent questions on that, so I think maybe people have the idea. But if you do need help, I'll be in my office this afternoon. I don't have office hours, but I'll be there, and so feel free to stop by. Our final is a week from today. We'll be doing our final 7 days from now. We've already talked about it, so does anybody have any questions about the condition of the final exam? We're going to continue talking about flood control measures and different ways that both structural and non-structural measures can be used to reduce the risk of economic damage due to flooding. So where we left off last time was talking about diversions, and the way that they change these 3 figures is for a certain flow rate, for a certain exceedant frequency, the flow rate isn't increased through the main channel. Increasing exceedance frequency is going to have more flow overall from the storm out of the watershed, but through the channel that we're interested in, the reason why this is flat is what it's showing is basically the 10-year storm and the 20-year storm have the same discharge going through the main channel because any excess flow has been routed through an alternate route. So let's take a look at a little video that kind of explains some of the ideas behind this. Let me just pause. Once the water level, see how this has kind of a top wall on it? So the water level's going through these openings, but when it gets any higher than that, some of the water is going to go over the weir still, but that is what's going to be forcing water through this the bypass channel. Is just no water will go over the weir till a certain elevation, and then any additional flow is going to be going through the bypass. So that's the significance of why they even bother having these openings, is it's forcing a restriction. So water starts going in the secondary route. It's generally straighter and of a reduced end value. So water is moving very quickly through this secondary channel because they excavate and kind of smooth the path. And this kind of structural measure is best for protection that's spread out, where you wouldn't necessarily be able to afford putting a flood wall around an entire town and all of its agricultural land. You could maybe put a flood wall around habitable structures, but farmland doesn't have quite the same value as buildings. And so if you're trying to protect a wide area, then this diversion is a great way to do that, because it's basically insulating the area between the inlet and the outlet of the diversion from having flood that ordinarily would occur. So they may have to reconfigure a few bridges, and you think about if you're suddenly putting a new channel in that's only going to have flow occasionally, then you need to have bridges that in the past it was maybe just a roadway because it wasn't a channel in the past. You're putting in a river that never existed, and it's only going to have flow in rare occasions. It may only have flow for a couple of days every 10 years or even less. So that's a diversion. And so any excess flow beyond a certain flow rate is sent to that secondary channel, which makes this section of the discharge graph horizontal. It doesn't change the discharge versus stage relationship in the main channel. So discharge is flow rate. So for a certain flow rate in the main channel, you're still going to have the same depth, and you haven't changed the relationship between water elevation and damage. It's just how much water is getting into the main channel for a certain return period. So spread out over a large area, high degree of protection. It's suitable for a variety of different types that are being protected. So where you've got mixed use in an area, meaning low value agricultural land and high value built up structures. And you can only do it in locations where the land area is available. And there are a lot of highly urbanized locations where maybe a diversion would be very, very beneficial, but they don't have the clear path to put a new stream, and so it's just not on the table as something that could be possible. Okay, flood walls and levees are a lot more interesting than either of the two cases that we've looked at so far. In the case of diversions, it only changed the exceedance frequency versus discharge. Last time when we were talking about reservoirs, it changed the same figure. But in the case of levees and flood walls, it modifies all three figures. You have to be able to do sketches like this for the final exam. I'm going to ask you a question. I'm going to say, here's the existing diagram. Tell me how this certain structural measure changes the relationship between exceedant frequency and ultimately the damage that could occur. So you have to be able to reproduce these sketches. So how does a levee or a flood wall work? So let's start with the hydrology. For a certain return period, the flow rate associated with that return period is actually, the dashed line is after you've put in a flood wall. So is it better or worse? It's actually making the situation a little bit worse by building up a flood wall and a levee, because what it's doing is ordinarily for a certain return period, the flow is moving more slowly through a channel. So flood walls and levees, actually you're enhancing the channelization, and so the water can move more quickly, and that leads to higher peak flow rates. So this is actually a negative thing. We wish it didn't happen, but it does. Additionally, look at the discharge versus stage. That's also a bad thing, that the curve is above the original curve of discharge versus stage. So think, for a certain flow rate, if you've put in a levee, which is confining the flow, you're kind of forcing the depth higher than it ordinarily would be. Because look at the water level here on the left side of the levee, and now the homes are lower. So if this levee wasn't there, the water would be spilling out into the floodplains, and the depth would be lower. So basically what we're doing is saying that ordinarily, the river would be all the way over here, but what we're going to do is put in a couple of walls. And so if it was originally going to be in there, but now we put in the walls, all that flow now is going to be forced up higher than it ordinarily would have been. So we're reducing the flow area, the depth has to increase accordingly. So we've done two bad things in a row. Increase the discharge by speeding the flow in its route, its path. It's like peaking more quickly, forcing the stage higher, but we do those two negative things because of the value we get here. So what it's doing is it's not allowing the water to get where the homes are. Here's some houses. They're not underwater because of the levee. So what happens is, for a certain elevation of water, the damage doesn't start like it would. Like in the past, before this levee was there, it only takes a little bit of depth before the damage begins. But now the water can get much deeper, and there's no damage, and then finally, when you get over the edge of the flood wall or higher than the levee and water starts to spill off the side, then it increases slowly at first, but then you get any additional flow is going to get you all of the areas that would have been damaged up until this point, the cumulative damage that's been avoided. If you have the water going higher than the levee, then it's going to spill out and completely inundate the area that previously had been protected. So that's why we have kind of a horizontal line here, is there's the immediate increase to the previous damage relationship. But there's a certain elevation where you won't experience any damage, and that's true here in Huntington. We'll look at a flood map in just a moment of the areas in Huntington that are protected by the flood wall that would have inundation in the 100-year storm if the flood wall wasn't there. So does anybody have questions about the levee and flood wall relationships? You'll be able to reproduce these sketches. You've got a week to practice these sketches. There's not that many of them. I think we're going to look at 5 different structural measures. So this is the third. Here's Huntington's flood wall. The flood wall in action, actually up to the edge of the flood wall. Okay, channel modifications are like dredging. Different types of things that we can do to enhance the flow, to make it so that it moves more quickly through the channel and has a higher capacity than it otherwise would. So channel modifications will reduce the roughness or increase the slope, reduce the length. Any of these things will make the channel more hydraulically efficient, and what they do is for a certain depth are going to have more capacity. So let's look at the figures. Now we've seen this one before, this first one of exceedance frequency versus discharge. In the same way that a levee makes the water move more quickly through the stream, and so therefore it's subject to a quicker time to peak, the same thing happens with channel modification. So for a certain return period or exceedance frequency, you've got a higher discharge through the channel than you did before you made the modification, because the water's moving more fast, so everything concentrates more quickly. That's why the discharge relationship's higher. But fortunately, that's more than offset by the lower discharge versus stage relationship. So what that's saying is for a certain flow rate, the water's not as deep as it was before. So if you've got a smooth channel, you've done this calculation using Manning's equation. You know, if you've got Q equals area to the 5/3, slope to the 1/2, n value, wetted perimeter to 2/3. So if n value is smaller for a certain flow rate and fixed slope, then the depth is going to be less than it otherwise would. So by making it more efficient at conveying flow, it brings the depth lower for a certain discharge. And if the depth is lower, then there's not as much damage. So you're going to be accumulating less damage to valuable structures and farmland and everything else that when it's submerged causes an economic loss. All of that's avoided because of this benefit. This unintended consequence, an unavoidable consequence, but the benefit of channel modifications is lower discharge, lower stage for a certain discharge. What about flood proofing? So flood proofing can include like waterproofing exterior walls so that they don't allow water to get into the structure, raising a building, you know, like jacking it up and putting it on stilts. I mean, more sophisticated than that, sometimes they'll take buildings and they'll like build a concrete frame underneath it, or sometimes they'll just put soil underneath existing structures, putting in a small wall or levee around a single structure, or even just giving people more of a direct warning so that they can park their cars somewhere else when a storm begins, or so that they can move their furniture to the second story of the building, lift like portable carpets and appliances and so on up to the second story of the building. You can reduce a lot of the damage through an improved flood warning system. So it doesn't do anything having to do with the hydraulics or hydrology, but what it is doing is it's saying the water level can be higher before damage can occur. So this isn't saying more damage for a given stage. It's saying actually for a certain depth of water, instead of having $20 million worth of damage, you'd only have $10 million worth of damage. You know, because people, due to the flood warning system, have moved cars out of the way, lifted their valuables up to the second story, or you know, there are fewer buildings that are becoming inundated for a certain depth. So this is a really cost-effective way if you don't have the land for a diversion or a reservoir, And if a flood wall is impractical, you can always do non-structural measures and get cheap reductions in damage, although it's not going to provide complete protection. Let's look at some online data. This is, especially because it's been wet recently, kind of interesting to look at what data is available through government resources. In just a second here, when this loads, we're going to see all the stream gauges in the United States. There's a lot of them. It looks like, wow, it's an infinite network. But if you zoom in on an area that we're familiar with, like if we zoom in on Cabell County, I think there's only 2 in the whole county. Okay, so here's the Mud River in Milton is 1, and I'm just hovering over it, and you can see where the water levels are right now in the Mud River in Milton. I guess we got a little bit of wet weather on, what day was this? Let me actually click on it. Oh, here we go. So we had a little bit of a bump. Let's see, today's the 19th, which is Friday. Here's Thursday, Wednesday. It must have rained Wednesday morning because it went up on Wednesday. I don't think the Mud River is regulated, meaning I don't think that there's any kind of hydraulic structures, like there's no gates or dams regulating the level of the Mud River. So it tends to be pretty flashy, as they say, very quickly responsive to streams. Whereas the Ohio River is regulated, and it has such a huge watershed area that its changes in water depth are more gradual. And they can be managed depending on what the folks at the Corps do with the locks and dams. So let's look at what's been going on in Huntington recently. Water levels were much higher earlier in the week and last weekend. You can see that they were near the kind of warning action level of 48 feet. No flood damage occurs, I think, until 50 feet, but it's been going down. We haven't had wet weather. And then it kind of projects where things are headed based on the weather report and probability of rain within the watershed in the coming days. So that data is out there for us. And what we can also look at is at the way other end of the spectrum in terms of time scale. Like this is looking, what we were just looking at was a couple of days in the past and a couple of days in the future of what's the water level at just a couple of locations in the county. So I think I counted them up a few years ago, and there's less than 100 gauging stations in the state of West Virginia. And we've got thousands of rivers. Most of them aren't gauged. So instead of being able to monitor in real time every single stream and how it might threaten property, this FEMA website allows you to put in an address, and then you can see what's the risk of flooding in the long term, like over 100 years, based on work they've done to delineate floodplains based on elevation. So let's look at campus. 1 John Marshall Drive, Huntington, West Virginia. Okay, so here we are. Zoom in a little bit here. Okay, so Zone AE is the area that is going to be flooded with the 100-year storm. And you can see this, here's the flood wall. And then this area of reduced flood risk due to levee, Zone X. So most of Huntington is low enough that it would be threatened by the 100-year storm if it wasn't for the levee. But then, there are certain portions of campus, like I think this is Old Main and the library, where it's on a little bit of a hill, so even if the flood wall wasn't there, they'd be all right up in Old Main. So we can create what this is called a FIRM, a flood information map, based on the location we're interested in. Let's see what that looks like. It'll take a minute to load. It just creates, like a printable map that has all of the key, and it's a scaled map. And so if you've got a house that you're interested in, like you're thinking about buying property, you could use this to understand how much your flood risk is, and then also to get an idea of the likely cost of flood insurance. So one area that I drive through pretty often on my way home each day is over here through Guyandotte. And so, Guyandotte is also protected by the flood wall. So here's the hospital. You go across the bridge. But then the flood wall ends. And on the other side, it's kind of remarkable. You've got a lot of closely packed houses and businesses. And then once you get outside of the flood wall, there are many fewer homes and very few businesses, because in this area, it's prone to flooding, and there's no protection from a flood wall. It's very expensive to get flood insurance. There used to be a website where you could actually get kind of a quote on flood insurance, and it's not operating in the same way that it used to. But in the past, type in an address and it would give me an estimate. In here, the flood insurance for a $100,000 house would be like about $1,000 a year. And on the other side of that flood wall, to get the same $100,000 of flood insurance is $4,000 per year. So quadrupling the flood insurance. And because the premium is so high, people can't afford flood insurance in an area like that. And so they're not going to build a home that they can't insure. Or maybe the flip side of thinking about it is you wouldn't build a home in an area that's such at a high risk of flooding. So with this tool, you can zoom in on any location where you want to know what's the risk of flooding, and it'll create that little flood map for you. So let's go maybe to Barbersville, where they don't have a flood wall in Barbersville. But let's see, Barbersville Park is next to a river, right? There we go. There's Barbersville Park. I think, yeah, there's Lake William. So here they've shown you what they think are the extents of the 100-year flood. So it looks like this is that school that's in the park. I think it's maybe like a mental health facility. It will not be flooded from the 100-year storm. So interesting tool. I briefly talked about this in class last time, the idea that when it comes to flood damage, there's more than just the cost of repair and recovery. The direct damage is the property that is lost when it's in contact with flood water. But indirect damage is also important to take into account when you're deciding whether flood improvements are justified. Because when an area is recovering from a flood, they're not going about their normal day-to-day routine. People aren't working, businesses are closed, and so there's the lost economic value of what they ordinarily would be doing, the opportunity cost associated with flooding. And it can also be, you could include in the indirect damage the cost of the emergency response, like the rerouting of traffic and the delay that it's going to cause to people when a road is closed. So any kind of structural or non-structural measure that prevents flooding is creating value by avoiding these damage types. Secondary damage is arising when people depend on the area that was damaged. They're not necessarily experiencing a loss to their property, but for example, if one of your suppliers has a flood and they're not able to provide you with parts, and so now your assembly line is out of commission, or you've got a delay in being able to complete a project because one of your contractors had their equipment is in an area that's been damaged by flood. So then you're experiencing secondary damage when it's that effect of other people that you rely on have experienced flood. Intangibles can be things like the loss of aesthetic benefits of an area now that used to have beautiful flowers, and maybe it was just well maintained, and now suddenly it's got a thick layer of mud, and even if you set aside the economic costs, which can be easily calculated, people sometimes have a loss to their living standards when flood damage has occurred. And so it's important to keep in mind the intangible damage. And then also, this is something that is important in West Virginia, because a lot of businesses have a hard time finding flat ground that isn't threatened by flooding. And so we have less economic development sometimes because of the threat of flooding. So if you can put in a flood control structure that avoids all of these negative consequences, then that would be kind of the benefits that would help to justify the costs. The costs are easy to calculate, but sometimes the uncertainty and intangible damage can be difficult to put a numerical value on. And so it's sometimes a little bit blurry whether projects are truly economically justified, but I guess we just do the best we can in quantifying these somewhat qualitative considerations. So here's a picture of an area that had experienced flooding, and you'd see there's just a lot of leftover mud, and it's not usually a high priority when, for example, roofs are leaking, or when you're trying to clear main intersections. Just a lot of mud on the sidewalks and grass being destroyed. It doesn't seem like a high priority, but nobody wants to live in an area like that. And there can be also health effects, because sometimes when there's a flood, especially in coastal areas that have a lot of chemical plants and pesticide manufacturing, when an industrial area that's on the coast experiences flooding, a lot of that pollution washes into the inland areas along with the flood. And they had big problems with that in Louisiana during Hurricane Katrina in 2005, where a lot of the chemical plants on the coast, they make things that are carcinogens, and they're not meant to be released into the environment, but they got washed, tens and hundreds of miles in some cases inland. And so there have been questions about if certain cancer clusters along the Gulf Coast were caused by the indirect effects of flooding. All right, that's the end of the semester. That's all I've got for you. What we're going to do is get together a week from today for the final exam, starting at 12:45. So we'll have 120 minutes. The exam will be a little bit longer than the 50-minute exams that we've had, but my goal is for you to have, about the same time pressure as ever. I'll make the exam maybe a little bit more than twice as long, and you're going to have more than twice as much time. So I think it'll be fine in terms of have enough time to go through the calculations. But let me know if you've got any questions on the project.